All right, so our main event, right? Our guest speaker is Barri, Barri, right? Right. Babow, she has an MS in Information Systems and an MA in the History of Science from the University of Wisconsin-Madison, and also a BS in Physics from Harvey Mudd College. She designed satellite software at Aerojet in LA and taught in the Astronomy and Computer Science departments in grad school. Intel brought Barri back to her native Northern California, where she has spent the last 20 plus years, is that possible? Working in information technology at various companies. And the topic is the amazing James Webb Space Telescope. So let's welcome Barri.
Hi, I'm Barri. I'm going to be talking about the James Webb Space Telescope, but you already know that. So let's go on. This is what we're going to be talking about. I'm not reading the slides. I'm trusting you guys can read, and I'll talk about other stuff. So, but let's talk a little bit of history, right? So we all remember the Hubble. There's some groups who don't. But just so we're clear, this is what it looked like. It was a nice little tube with sunscreens out on the sides of it. You know, the primary mirror in front, the secondary mirror back here in the middle-ish. So overall, it was about an 8-foot mirror. It was launched in 1990. I happen to be teaching in the University of Wisconsin-Madison astronomy department when this launched. And I happened to be working for at least one professor who had instrumentation going up on it. It was super fascinating being there during that time with everybody holding onto their seat of their pants to see what was going to happen with those optics. So the optics got repaired in 1993. They put some glasses on it, right? I'm not going to go into the details of what happened. If you don't know, you can ask me afterwards. But in general, this instrument was looking mostly invisible with a little bit on either side, a little bit of UV, a little bit of near infrared, but mostly it was focusing on visible. What do we see? That's like what you and I see when we walk outside. But it was above the Earth's atmosphere, right? So we got some great images. So for example, we got Voyager doing a flyby on the left, and we've got Hubble on the right. That's pretty amazing difference. Hold this in mind because we're going to revisit it with James Webb. So the James Webb, the JWST, isn't replacing the Hubble, it's the successor. So the Hubble will be up there running for as long as it runs, doing its mission, its science, all of that great stuff. The JWST is just the next one, the next space telescope. So after those optics were repaired, it's like, hey, maybe we want to fix that and not make that same mistake again. Yeah, great thinking on their part. So the reason for going with infrared, which is what James Webb is looking at, is because they wanted to look at stuff that was old, distant, faint, things that the Hubble doesn't do a great job of seeing because it's looking invisible. It's looking invisible. Great, I'll remember that line. So now we've got a 24-foot mirror compared to that 8-foot mirror. We've got the instruments looking at some red, but mostly out into the infrared instead of focusing on visible. So now, are you wondering, why do we need the bigger mirror and why are we going with these wavelengths? Wow, I can almost spell. No, it got cut off. So this is what we're going to cover on the James Webb, right? The size, the redshift, some more about the mirror, all this great stuff. So let's dive in. So why is bigger better? Oh my gosh, I hope y'all in the astronomy club know why bigger is better for a mirror. You're capturing more light, right? If I'm looking at something this, this big, I can capture a lot more light than if I'm looking at this big, right? That's just the nature of optics. You get better spatial resolution. It's the same thing. I mean, I'm trusting you guys all know these sort of basic stuff. So the result is they're going to be able to see farther and farther away, and they're going to have more and more clarity of what they see. So These mirror the James Webb 6 times the area of Hubble's. I mean, that's no small feat, right? This is going up into space. 6 times the area of Hubble, and they're expecting it'll see 9 times fainter objects. So put it in perspective, a nice little diagram. Thanks, NASA. You see the person going, and the Hubble one is this tall. But you know, that's a great shot. You all know why there's a hole in the middle for the secondary to reflect into the instruments. I'm trusting you, because other audiences I've spoken to, I just don't even mention that, because that's going to go right over their heads. What? There's a hole in the middle. Why? Okay, so now let's revisit this. Voyager versus Hubble. And now we have a Hubble versus a James Webb. First of all, I gotta say, they weren't exactly expecting to be able to focus on stuff this close. So it was a little bit of a miracle that they could even focus this close in space. And it's totally cool, because now we can see the auroras at the poles. Those just light up, which is beautiful. So, you know, they're studying this to understand what they see. It's the same level, at least when I look at it. I see sort of the same level of clarity, but it's a totally different view, because it's a different wavelength. So it will, you know, tell us more about chemical composition and that sort of thing. The layers where different items are in the depth of the atmosphere. Okay, so we covered size. Let's talk about redshift. I'm muted. Sorry, I've got a different way of showing it. That was a good car going by. Right, that rise in pitch and then the drop in pitch. So we can see it visually here. I don't know if you can see my cursor, almost maybe, but over here we've got you know, an ambulance coming towards us, and those wavelengths are getting squished coming into our ear. And then when that ambulance goes past us, that wavelength spreads out, so that pitch is going to drop. That's how sound works. How about for light? It's going to be the same thing, right? So this is a pretty little diagram that says, hey, if it's coming towards us, it's going to be squished together. And as it's going away from us, it's going to be shifted towards red. Now, look, when they came up with the phrase redshift, nobody thought about the other wavelengths in the spectrum. They didn't matter. All that mattered was, you know, you go from purple on one side to red on the other side. So red made sense. So now we get to Hubble's law. Again, this is a topic. You want to talk about this with me afterwards? We can talk about it afterwards. I'm not going to get into detail other than saying this. Those objects that are far away from us, they're moving quickly away from us. And the farther away they are from us, the faster and faster they're moving away from us. So that's Hubble's law. Well, that's great. But how are we going to know how far away something is? Don't we need a metric in here so that we can measure that change, that frequency change? So, yep, there we go. Longer and longer, red. So we know the star composition now. Big thanks to Cecilia Payne. She figured out that we can see the spectra because she figured out the stars are mostly made out of hydrogen and helium. So that's redshift. That's measuring how much the hydrogen and helium lines have shifted from a laboratory standard further and further to the red, or in the case of James Webb, way past that and into the infrared, which totally cool. Or in this case, kind of hot. So here's the diagram that the European Southern Observatory put out. Laboratory spectrum, these are some of the hydrogen and probably helium lines in here. I'm pretty sure those are the hydrogen over there. And when you look at the nearby galaxies, they're shifted a little bit over. You look galaxies farther away, they're shifted more over, but we can measure how far that shift is. And then what they call very distant galaxies, which was way before anybody was messing with infrared, they're like, this is really, really far away. Now with the James Webb, this is just quaint because this is nearby, right? The scale changed once we had the James Webb, but this was their view, and this can be measured really accurately. So we can get an accurate read of that speed. So taking this back, when we talk about the Hubble and we talk about visible light, that's just a small part of the spectrum. And the James Webb was just barely on either side of that visible light. And now for the Webb, they pick up a little bit of the red, and then what's considered near infrared over here, and then mid infrared over here. This is far infrared, which it doesn't go to. But that's a heck of a part of a heck of a breadth of the spectrum to be covering. Where are we? More details about the mirror. I love this picture. This is like a Where's Waldo picture. Look, here's Waldo over here. There's a little person working on this, and there's the telescope, and a couple of the mirrors are over here, turned back, like this isn't completely unfolded. That's a whopper. So they're gold. Did you guys know that? They're coated in gold because gold works well for reflecting infrared light. Pretty sure the Hubble was some type of aluminum, because aluminum works well for visible light. They're hexagonal, so there's that high fill factor, right? They fit together without gaps. If you think, what would this look like if they had made circular mirrors, right? There'd be a whole bunch of gaps in there, and then they'd really have a heck of a time putting those images together. So they went with that hexagonal for that high fill factor. And then there's actuators to adjust the shape of the mirrors. Remember Hubble and the optics problem that they couldn't do anything about? This was a response, right? We're going to put actuators on it so we can flex the mirror to a certain extent, and get focus, right? Up here. So the struts, I forget if they consider this 3 or 6 actuators. I forget which way they call that. And then, where it sits on the substrate, all of that. So that's sitting behind each mirror and can be controlled. They solved one problem from Hubble. Sorry, I shouldn't laugh about that, but at least they got that. So 18 segments. This is a beautiful quote that says, if the mirror were considered the size of the US, then each mirror segment would be the size of Texas, and they'd have to adjust it within 1.5 inches. 1.5 inches over the size of Texas. I mean, just phenomenal accuracy and precision. So let's see if this plays. This is showing the mirrors actually behave as 18 separate mirrors. Anytime in here, this is going to start, or I'm going to go on to the next slide. There we go. So those 18 mirrors had to be focused. So this is a little GIF showing them being focused. I'm not talking about the issue. I'm completely coasting past the issue of they didn't know which piece of light came from which mirror. First, they had to figure that out, but I'm skipping that discussion. They figured it out, right? So this was them adjusting those mirrors into that 1.5 inch over the size of Texas to get a clear view. Let's go on. And then this is them taking those 18 images, and now they've got to focus them in the center so that they can be sent off the secondary mirror into the instruments in the back. Pretty cool stuff, in my humble opinion. They're still thinking about it. They're going to get it. There you go. There you go. They got it. So Now let's talk about infrared. You know, we're all warm, right? We all give off infrared. That's what it looks like for our hands. So that red stuff is right about 98 degrees. And then in our fingers, it gets cooler. So they made it, you know, go to yellow. And then at the tips, it's going towards green, right? I'm hoping you guys are familiar with the phrase false color image. This is a false color image, right? But this means we can't have the James Webb nearby. It can't be on Earth. That's why there haven't been infrared imaging before, because we're such a massive glow stick here on Earth. You can't take images of space in infrared unless you get away. So the JWST has to be cold, minus 364, or if you like Kelvin, 53 Kelvin, you all know 0 Kelvin means all motion stops. So 53 Kelvin, that's pretty darn cold. So how'd they do this? A sun shield, 5 layers of sun shield, right? Again, this one is an easier Where's Waldo. It's a lot of them down there, right? But that's gigantic. We're well past the size of Hubble going up in the space shuttle. Oh, there's one other thing that we need to do. We got to get it far away from here. It can't be anywhere near us, right? So if we look here, we go, okay, we're 100 million miles to Earth from the sun. That's a good distance. We're good. And now if we look here, Hubble is orbiting at whatever, just shy of 400 miles off of Earth, right? The moon is out at whatever that is, 250,000 miles. And so they're putting the Webb out at Lagrange 2, L2, near L2. We had a big discussion over dinner about this. Right by L2. A stable orbit point 1 million miles away from the Earth. So let's take another look at this. So as the Earth is going to go around the sun, the James Webb is going to go around with us in orbit. So it's not orbiting us as Earth, it's orbiting the sun with us. You all knew that, right? Yes. Oh, good. Oh, I love it. You guys are going to totally spoil me for all my other lectures where they're like, Barry, we don't understand what you're saying. Okay, so here we go. We got the hot side and the cold side. So the hot side, we've got our solar panels. Those are good for keeping the energy up. The communications antenna. Yes, that's in gigahertz. The communication is done over gigahertz frequencies. The computers are over on this side. The steering is over on this side, and that sun shield is here, protecting the instruments, the primary mirror, and the little secondary mirror down here. Okay, so some fun stuff. Here they are side by side. This is going to get into a rocket and go in space. And there will be no repairing of that. There is no way to send a mission to fix anything. It's got to work. So the Hubble was the size of a school bus, and it just had to unfold those solar panels. That James Webb is the size of a tennis court. They're sending a tennis court into space. And so how to get out there? Again, I'm expecting you guys to know this answer. Folded, origami, inside the nose of a rocket. In the end, the size of this space in the nose of this rocket, pretty much close to the size of the cargo bay of the space shuttle. It's pretty close. I mean, it's within like a foot or two in any way. But yeah, they folded the heck out of it and threw it in here and sent it up into space. It took 30 days to get out there. It took 2 weeks to unfold. It was sent out December 24th is when it launched. So of What year was that? What year am I in? 2021. So January of 2022 is when it got out there. It took months to adjust everything. And again, as you guys all probably know, 300 single points of failure. If any one of those more than 300 items had gone wrong, we would not have any images to show, and I would not be talking to you. It would have been dead in the water, a beautiful piece of art, 100 million miles away. I don't particularly like this go of it. I've got a little video that I'm gonna show instead. I thought this shows it really nicely, right? With the tennis court sunshield starting to unfold. It's got 5 layers on it. So it's going to show that first it unfolded it and then it separated those layers. So it takes a little bit of time. What are they going to do next? I'd unfold the mirror, but it still appears to be thinking about something. Oh, they brought down the secondary mirror first, and then they unfolded the mirror. This wasn't without controversy. Big government project. So let's start. What's in a name? James Webb was a NASA administrator. I don't know about you, but I've never heard of another satellite telescope, space telescope named after anything but a scientist. So that was kind of controversial. He was the first NASA administrator. Okay, but still, he was an administrator. That was kind of dicey. There were about 1,200 folks who signed a petition that said, oh, by the way, there was some serious abuse of the LGBTQ staff. So either he was ignorant and not doing his job well, or he was complicit and knew that it was going on. And so they're like, hey, NASA, come on, change the name. To which NASA said, no. Thanks for playing. No. It was costly. It was late. The research I did said it was supposed to launch in 2007. I couldn't find a price tag for that 2007 launch date, right? Because this started in 96. So you think 11 years, that probably should have been enough to build it. It wasn't. In 2014, I found that there was a price tag of $5 billion. Okay, so now we're 7 years later. And then 7 years after that, it finally launched for the tune of $10 billion. Woo, that's a lot of money. It was a consortium. So it wasn't just NASA, it was also the Canadian Space Agency and the European Space Agency. So to be fair, those 300 points of failure and being completely inaccessible, I kind of appreciate that they took the extra time to make sure it all worked, because there was no going back. There was no chance of doing anything else. What else? A little controversy about micrometeorites, right? That there'd be little things that were going to hit it. They knew there was going to be little things that hit it. They knew that was going to happen. There's stuff out in space. They knew the mirror was going to get scratched. It was going to ping. They were expecting that. The problem was, right off the bat, something hit it that was way bigger than anything that they expected. That sort of took their breath away. The articles from around the time show a certain level of shock and remorse. So what happened because of that larger micrometeoroid hitting was they had to realign the mirrors. Right, they lost a little bit of clarity, which they're like, okay, we can live with that little bit of lost clarity. But they had to realign the mirrors. And moving forward, their expectation is, by the way, when there's known meteor showers that are coming in, we're going to turn away. As much as possible, they're going to turn away. So the deal with that is those impacts and those maneuvers that they have to take affect the longevity, because that's using fuel, but it's also degrading the mirror, right? Those two things together, the fuel loss and the degradation, that's a problem. And I was thinking the next space telescope, they would basically do a different design to come up with it. Well, it ends up the next Space Telescope is actually pretty small, quite a bit smaller than this with a totally different mission. So we'll see what happens. But they do have a name for it, the Nancy Grace Roman Space Telescope. So wide field telescope. So that's cool. They're making headway. I don't know if you guys really need this one, but we'll talk about it for just a sec. We'll start over here. Basically, I'm going to explain why I'm talking in light years instead of miles, right? Because miles just get so crazy to talk about. So 100 million miles, that's 8+ light minutes. Where we go down all the way here to the bottom, I'm cutting to the chase at 13.4 billion light years. That's 76 billion thousand miles. Yeah, just hard to talk about. So we're going to go with light years. You all ready? You ready? You ready for the images? Yes. Okay, we're going to start with small. Oh, these are the small objects. These are the cats. Don't they look like little galaxies? Okay, we're going to look at some of the small objects. A couple of the planets. I'm not showing Jupiter again. A couple of the exoplanets. So here's what's going on. On the left-hand side, this is a artist rendering, simulated image. This isn't real. Nobody's gotten a picture like this, or if they do, I haven't seen it. And then we're seeing what the near infrared camera saw. So this is sunlight being reflected over here. And down here is Hellas Basin. I mean, we might think the Grand Canyon is big. Hellas Basin is 4 miles deep. That's why it's dark. It's, you know, there's sunlight, but at 4 miles deep, there's not a heck of a lot of sun coming down there. So nice image. Again, this is near infrared. So this is basically a heat map. Uranus, these images just came out recently. So they are showing some of the moons here. And you can see the rings. This is supposedly showing 6 out of 27 of Uranus's moons. So nice image. Or if we want to see it closer up, this is a better image. Uranus is one of the oddest planets around. It orbits this way, going around. So what's happening here is, I don't want to say the wrong thing. It's spring. It's spring there. Yeah, this is the North Pole that's being shown. NASA's claiming that this is showing 11 of the 13 rings. I tried counting. They got way too fuzzy for me to be able to count that well. But it's the most beautiful image of Uranus that's been captured, at least that I've seen. So we're going to go back to Neptune. On the left, that's Voyager. On the right, that's Hubble. And when we go to the James Webb, this is showing it again in a different light. You can see some of those moons in the rings. You can see the rings, the aurora or dust that's around it that's glowing. Okay, we're moving on. Exoplanet. I'm only showing 2 of the exoplanets that James Webb has observed. I know they've observed at least 1 more, maybe 2 others. This is an illustration. We don't have a way to take a direct image yet of an exoplanet. Just for anybody who's not super familiar, the concept for an exoplanet is it's any planet that's not orbiting our sun. It's just a planet orbiting some other star. So this happens to be LHS 475b. That's a red dwarf star. So this is showing the transit curve. I'm not sure if you guys have played with these, but it says, look, we can see the light of the star, the light of the star, the light of the star. Oh, it dipped. It dipped, it came back. And so that tells the folks who compute this how big that planet is. In this case, that planet is about 99% the size of Earth. It's a rocky planet. There's a convenience here for finding exoplanets and being able to take images like this. Its period is 2 days. So it's orbiting really close to that red dwarf. It also helps that it's orbiting a red dwarf, which is cooler than, say, our G-class sun, right? So since it's cooler, you can see better against it. If it were a super bright sun, that planet would be lost in the glow, right? So that's really important for this. And so since they have spectroscopy available, they went ahead and said, let's look at specific wavelengths and we can see if we can figure out what the atmosphere is made out of, right? So these white dots are the observations from the spectroscopy. So different wavelengths to get different values. And so they mapped it against the green, which would be a methane atmosphere, the purple, which would be a carbon dioxide atmosphere, the flat line, which says no atmosphere. And they looked at it and went, huh, we don't know what the heck that is. But, you know, they're trying to model it. So got to give them credit for that. Not like anybody could have done this before, so that's impressive. So GJ486b, this was just published on May 1st. This was just published Monday. I thought you guys would like to be at the forefront of these breakthroughs. Again, another illustration. Again, another red dwarf with a closely orbiting planet. This planet is a little bit bigger than our Earth, 130% of its size. The orbit is like 1.5 days, 1.5, 2 days. Okay, so they did this. So I'm skipping the transit because you guys have now seen a transit. But this is another model where they're like, okay, let's try to model what this data is at different frequencies. And they're thinking it's either a star spots model. I don't know about you, but I've never heard of star spots. That basically says that there's hydrogen and oxygen coming off of the star. Oxygen coming off of a star? Scratch, scratch, scratch. Pretty weird. Or the water-rich atmosphere in blue. So basically they're seeing H2O, or they're at least seeing hydrogen and oxygen. And now they're trying to model it. And then they're going to try to figure out, is it something coming from the star? Is it something coming from the planet? So they're just working it out. Like I said, this just came out May 1st. I love how they think those models go with those points. Somebody must have decided this was good. I don't see it. I'm obviously missing some imagination. Okay, let's talk about stars. One of the instruments on the James Webb is coronagraph. We were talking about the annular eclipse that's coming, right? Which is basically an annular eclipse is basically putting a coronagraph over the bulk of the sun so that we'll be able to see the outside of it, the annular, like a donut on the outside. So they basically used their coronagraph to block out where the star would be in the center because they wanted to see what the disk was outside of it. So the orientation for this, I'll try to do this so folks playing at home can see. I'm holding up a piece of paper. So the orientation for this star and its disk is this, right? Not this, because then it would look like a platter. It's this. So they're looking at it edge on in different wavelengths and saying, oh, that blue one is showing the fine dust particles. So it's cool. I don't know what it means other than they said it looks like fine dust, but I had never really heard about stars having dust around them to this sort of extent. So it's interesting, especially interesting that it's in a single plane like that, right? One would think that it would be three-dimensional around, like a globular cluster. This obviously isn't like that since that dust disk is in a plane. One could think in the end it might end up looking like Uranus or Saturn or all of those giants that have the rings around them, right? That those would coalesce into rings. I love this image. Look at how evenly spaced those, not quite rings, but sort of rings are. We never see stuff this regular in space. So what's going on is this is a binary star system with an 8-year orbital period, and every time it hits its closest approach, it's sloughing off material. And so you get 8-year slough, 8-year slough, 8-year slough. Wolf-Rayet is a type of star. It has heavier materials than what people think a regular star should have. That's how they got the name Wolf-Rayet. So this is a binary with those regular periods. This is another Wolf-Rayet, but this one is very, very different. This one is in the later stages of its life, and that is chaos. It's a single star, and it's blowing off its material. The expectation is it's going to go supernova, right? And so they're looking at it and going, wow, how does this play out? How does it work? Let me see if yeah, this is another image of it. I don't know if you guys know how the astronomers figured out the different star classifications, right? Because we don't have a billion-year history to look at stars and figure out what the life cycle of stars is, right? So they do these catalogs and try to figure out what's the evolution of the stars over time. What's the natural progression, right? Because some end up supernova, some end up neutron stars, right? Different masses end up going to different endings for their lives as stars that are nuclear reactors. I think they're studying this one, and this is the first time that I've seen them talking about, we know this baby's going to blow. We just don't know when it's going to blow. And I'll bet they're going to end up doing a whole bunch of surveys so that they can put together a timeline of what it looks like, because they want to know how much of this gas and dust remains after the supernova, what gets blown out, and what still stays around for other things to form afterwards. So I got to come look. Oh yeah, it's way better on my computer. Sorry. The colors are way more stunning on my computer. Ah, sad. But it's still beautiful. It's still beautiful. We'll go with it. Let's talk about some galaxies. Again, we've got the Phantom Galaxy. This is ye old spiral galaxy, presumably like what we're in. We've got Ground versus Hubble, and then we've got Hubble versus James Webb. To me, this is stunning, where all of this dustiness from the Hubble that the visible light can't shine through, now we can see so much more through it to see sort of the bones of the galaxy. I'm going to make it bigger. This shows it even bigger. So these red spots are they're the protostars. They're what's going on. The stuff in the center are already stars. They're already cooler. Again, I don't know how well that resolution is showing over there. And somebody thought it would be great to do it in hell colors. So I think the reason they did it in hell colors is to highlight where these holes are in the structure of the galaxy, because where these holes are where the stars have formed and that stellar wind has pushed that dust away. Weren't we talking over dinner that 30-minute time difference because of the solar wind? Somebody remind me, right? Yep. So I think these colors make it less distracting than these colors, where it's all pretty, but it's prettier to look at the stuff that has, you know, the different nuanced colors in it. It's all false color imaging. So none of it is a visual it's all a visual representation with somebody picking the color palette, because it's not in the visual light that these images are taken in. But I loved it. Nice hellscape. Great, thanks. Yeah, I mean, that's what I call it. Although the headline that I saw that went with it was, I think it did call it a hellscape. Yeah, the shades of red, which the fire, yeah. Which again, it's not, the colors aren't looking as great as they look on my screen. Sorry, I can't turn my screen around to show you.
If that's solar wind, then where's the star? Are they the ones that are lighting it, pushing it away, or, you know what I'm saying?
Yeah, it's hard to tell in here, right? This is quite a distance away. It could be these guys in here. On my screen, these look blue, which means that they're a little bit older. In here, there's a whole bunch of little dots. Yeah, in here I can see some dots, right? Because it's the protostars that are the red, and so they're in the middle of the veins. Okay, let's go on. Cartwheel Galaxy. This is obviously two galaxies that collided. Just saying. I mean, I knew you would know it, but somebody had to say it. This is how it looked for Hubble. This is how it looked in mid-infrared. Wow. That really got rid of the dust. And then this is how it looked when they put the near infrared and the mid infrared together. So it reintroduces some of that dust back into that image. I got to tell you this. Do you see this? How there are 8 spikes? Well, no, it's 8, whether or not we can see them. There are 8. That means it's James Webb. It's got 8 spikes. If you see an image that has 4 spikes on it, and somebody tries telling you that it's the James Webb, you can confidently tell them that's the Hubble. Okay. This is 5 galaxies, Stephan's quintet, of which 4 are interacting with each other. That was the Hubble. Not nice of them, but they turned the image upside down. This is it in mid-infrared. This is the composite. Again, these big bright stars, these are in the foreground. Those aren't out with those galaxies. They went on. This is the integral field units where they can slice and dice the images spectrum-wise and space-wise. So they basically looked at these little spots here. They basically isolated these little spots here. And because I know Greg too is going to ask me, they didn't mention that this was done with the microshutter array. They said it was done with the integration field unit, the IFU. But basically they could take this part and say, oh, look, we see the spike for iron, argon, neon, sulfur, more neon, more sulfur. And for this the big part, the active black hole, they're like, oh, look, there's molecular hydrogen. Molecular hydrogen. That means it's not ionized. That's pretty interesting. One would think at some of these temperatures that stuff would be ionized and some different stuff. So basically, this is starting to really show off some of the power of the James Webb, where they can isolate a spot in space many light years away and get this sort of detail. They took it one step further and they said, let's take this one spot and look at a particular space and see how it would look in a visual representation, right? So this is how the atomic hydrogen looks. That's its distribution. That's the iron ions. That's the atomic hydrogen and the molecular hydrogen. I mean, come on, we couldn't have done this stuff even a couple of years ago. They wouldn't have been able to do this kind of image processing on anything, let alone a telescope 100 million miles away. So this is pretty astonishing science that they've pulled off here. Let's go on. Oh, and this is the last image from the Stephan's quintet. I love this one. They said, we've got the James Webb composite. It rocks. Let's throw in the X-ray data and see what the heck is going on. So they put it together with the X-ray data. And I have to tell you the number because this number is crazy. They figured out by looking at this combined image that there's a shock wave because one of the galaxies is weaving through the others at a cool 2 million miles per hour. And it took combining that infrared with the X-ray to be able to pull all of that together. I think this is the future where the JWST imaging is going to go, where they start combining it with visual, with X-ray, basically with anything they can get their hands on to come up with new understanding of what's going on underneath it. I thought it was cool. Okay, the next three I'm going to buzz through. This is the physics at high angular resolution in nearby galaxies survey. Is that what they called it? I think they called it survey. FANGS. So this was the folks at JWST agreeing that there were about 20 or FANGS, I know, isn't that great? Saying that there were about 20 galaxies we could see that were barred spiral or spiraled. People think the Milky Way is a barred spiral, right? The issue is back to that planar view, right? What's our view of the Milky Way? It's about here, right? So they're doing FANGs because there's all these galaxies that they can look at this way and go, look, this is how it looks. Maybe we look like that. I think of it as being my cats looking in the mirror. That's how I look. So this is one of them. It is cleverly called the Great Barred Spiral Galaxy. Like that is literally the name given to it, aside from the New Galactic Catalog. But this is one of them. Pretty cool. This is another one. This one didn't have a name other than its New Galactic Catalog designation. But again, a different approach. I find it interesting that it's got sort of this open space here and then more nuance farther around, including these stellar nurseries, right, way out in the dust. And then the last one of this set, again, they didn't give it a name. It's just another barred spiral galaxy. But I think that's where they're going with it, is they want to look at these ones that are that high angle to us to go, what do we look like? What could we look like? This is how these other ones look. This is how the other ones, you know, have changed to get to where they are now. Okay, dust and other clouds. Oh, some of these images I know y'all have seen. This is the Carina Nebula from Hubble. So this is visible in near infrared, but both from the Hubble. And then this is a piece of it, a small piece of it from the James Webb. So let's go back a sec. So basically what we're seeing here is a whole lot of dust and we can see some granularity and we can see, you know, some of the stars and some stuff poking through. But here, I mean, this is a really dusty image from Hubble. Sorry, Hubble. No disrespect meant. But this blows a lot of that dust away. And now we can see where there's holes starting to form in the dust. Again, this would be where stars have formed and blown out that that dust and that gas away from them in that stellar wind, basically. So that's the near cam image. They did a composite image. Since the other one was near cam, I mean, the MIRI adds a little bit. You can see a little bit more of the glow happening. The stars being formed to me stand out a little bit more. Let's go on. So this again is from Hubble. This is also called the 8-burst nebula. The funny thing in this image is this isn't believed to be the star that's actually bursting. Or it's not. The star that's bursting is supposed to be down here. It's hidden, but they said this isn't it. This is perturbing the heck out of the nebula. Don't get me wrong. It's the one causing issues. This is how it looked for near infrared. This was from, this was part of the first images that came out in July of 2022. This is how it looked in mid infrared. And July of 2022, when the James Webb released this, they said, look, you can see them both together. Come on, it's funny. In December of 22, they're like, oh, actually, now we've had the time to put them together. It's hard. It's hard to do the image processing. This isn't developing a photograph in a darkroom. This is playing with bits on a computer. So the reason they pointed out these two special segments is because it's interesting to have one nebula where the gas and dust is being blown off in straight lines off the edge. And in another place, it's just a mess. It's just a whirl of chaos. So it's like, well, that's interesting. So that's why they pointed it out. Pillars of creation. I mean, this one is such the hand of the creator coming up. So again, this was Hubble, very dusty view. This one, they just started right off the bat with a composite. What's crazy here is seeing the stellar nurseries just screaming out of these images. These little orange guys here, the little protostars that are developing. And then basically the fingers, so to speak, are getting eroded, right? Because like when this star ignites, it's going to slough off its dust. And so this piece over here will now be clear of that finger. Likewise, when these start igniting, then that will eat away that part of the nebula. I love how many stars and galaxies and whatnot are visible here. I mean, that's just stunning. Okay, this is the last image of the nebula. This is a protostar in the center, and it's throttled on either side. Like, think of somebody wringing its little neck. It's for whatever reason, it's choked in the center here. There was no explanation that I saw of why, and so it's sloughing off its gas in these cones on either side of it, like an hourglass, right? But it's pretty cool. Okay, the last few slides. This is where we get to Greg Chu's favorite part, the microshutter arrays. Life is good. This is what Hubble saw when they did the deep field, and those different squared off boxes are what James Webb is gonna look at. So let me just point out, do you see the density of stars here? They're not stars. Sorry. The density of objects here. Do you guys know how deep fields are taken? Yeah, that it's taken by pointing at nothing in the sky and taking an image and going, oh my gosh, there was something there. Right, that's how these are taken. So this is the density of objects looking at nothing that Hubble saw, and then the James Webb is going to look at these little boxed off areas. So this was one of those boxed off areas, and that density is just as dense as the Hubble for that whole field of view. And this is where the microshutter array comes into play. They said, let's start here at the top. This little piece right here is 11 billion years. This little piece here is about 12.5 billion years old. This piece, 13 billion, and this over here, 13.1. So before James Webb launched, the expectation was the universe was 13.8 billion years old, and now they've found something 13.1 billion years old. You know they're not going to find something that's from the beginning of the universe because there was no light to see. It's like walking into a dark room and going, I can't see anything. Well, yes, because nobody's turned on the light. It's exactly the same thing. They can only look back so far because you got to have something to look at that's 13 billion light years away. Otherwise, you can't see it. You all familiar with gravitational lensing? That's what's going on in here where you see these elongated galaxies. They're not really elongated in reality. They're just being spread out because of gravitational lensing. So this is what we were talking about at the very beginning about the spectroscopy and being able to say, okay, how far out is that shift? How far out is the red shift, and what, you know, and what are we seeing? And you can see the shift keeps going and going and going, right? So this was the first deep field from the James Webb. This is the more recent deep field where they looked at this part of empty sky and saw all of that stuff. And this is where, I mean, the stuff down at the bottom is about 10 billion light years, but at the top, they're at 13.2 billion light years. The expectation is that that is when the universe was less than 400 million years old. The number I saw ranged between 220 and 350 million years old. So just to say it, I'm pretty sure they've discovered that these galaxies are better formed and bigger than they were expecting for how old they are. So there's going to be some revisions to the Big Bang. There's going to have to be, because what they weren't expecting them to be this big. And this graph is different than the other graph because this graph is showing the Lyman break. So I gave Greg too a file that's the resources. There's no reason to give you guys handouts because it's all hyperlinks. So hopefully someone will send it out. And one of the last links is talking about the age of the universe and the Lyman break and why it's so important. But the Lyman break is what was used to date these objects, these galaxies. I'll leave it at that. There we go.
Question?
Yeah.
Why does the auroras on Jupiter show up better in infrared?
I expect
I'm surprised
because
at
they're warm,
Repeat the
and so
question.
they're not showing invisible.
Mary, repeat the question.
Oh, sorry, repeat the question. Why are the auroras showing up on the James Webb image for Jupiter, but they don't show up in visible light? And so my answer is, I'm pretty sure it's because those aurora are warm, and so the visible light isn't capturing them. Even on Earth, I'm not sure if we were in space how visible the auroras would be as far as dustiness showing. Right, we can see the electric activity and we can see the auroras in the sky, but from space, I don't know if our aurora show is going out in space.
Are all the adjustments made, quote, from Earth, or does the telescope know that it's out of focus and needs to focus?
Okay, so the question is there any brains on the telescope itself so that it knows to adjust itself, or is everything done from Earth? The answer to that is everything is done from Earth.
Okay. No internal brains.
I have not heard of there being any brains
Yes,
on
yes,
that telescope.
yes.
Yeah, they're gonna upload ChatGPT. Any other questions? Yes.
So the light spectrum is shifted up into infrared. That means that something else, ultraviolet, is shifted into visible, which Hubble should be able to see. Is there anything interesting in there?
Yeah, okay, so the question is, since the objects that the James Webb is looking at are in infrared, and we can see them, that means the visible light would be, the X-ray light would have shifted up into visible, so why can't we see this stuff in visible? The answer to that has to do with the intensity.
Hubble
So
could
the
see it.
Hubble, okay, but to be fair, the Hubble does see something. So like we could look at Jupiter and Neptune or whatever from Hubble, right? So Jupiter, we can see, right? We can see it invisible and we can see, I know what you're saying, but the issue is
It's just too dim.
the Planck black body radiation curve.
Okay.
The issue has to do with the black body radiation curve and where's more of the peak of that curve of what's visible, what's shining through, right? I'm giving off infrared, can you see it?
Yeah, some of the things it sees as visible probably started out as ultraviolet.
So I just want to talk to that for a second, that's summing up, because there is an interesting part of this that I didn't discuss all that much, and that is any of us can get this data. It's public domain data, and there's actually a woman in Modesto named Judy Schmidt who's become a rock star at NASA because she has done some of the very first imaging. It won't show on the Webb Telescope page because she's not an employee, but it's a woman in Modesto who's taken an interest. She's like a graphic designer and amateur astronomer, and NASA's like, we love you, Judy, because she's done these great image processing. So the same names keep coming up over and over again. A lot of these, again, another part of it I didn't talk about is NASA is totally cool with us showing these images. In fact, y'all could have paid me thousands of dollars and I still could have shown NASA's images. All I had to do is give credit for them, which I did. On the first slide I showed the images, I said credit, NASA, CSA, everybody. And then on some of the other images, I did the credit plus, and then I listed all of that. I didn't call it out. There's two people whose names keep coming up over and over again, Alyssa Pagan and Joe De Pasquale. Those folks must be rock stars. They're the ones who actually take the final data and create those colorful images. They're the ones who are picking the color palettes and they're trying to be consistent over image after image after image, so that we all get used to that reddish orange being the nurseries, that bluish being the older stars. Like, these people are rock stars to me. And I just think we should sort of all be appreciative that they're doing this work for us, because it is not a slam dunk. It's got to take hours, multiple hours to create it.